Today we're going to be talking about section 5.3. 5.3 is about finding x values in normal distributions. So when we're looking at the standard normal curve, a lot of times we're trying to find z-scores from x values. But that's not always the case. Other times we're actually doing exactly the opposite thing, where we start off with the area or the probability, and then we have to find the z-score that came from that, and then maybe we need to go all the way back to the x value. In other words, sometimes we have to work backwards in these problems. We have an example. Find the z-score value that has an area of 0.2236 to its left. When we say to its left, what we mean is that, remember that the standard normal distribution table gives us areas to the left? So we're going to look for this value, 2236, in the standard normal table. We're not going to look for it at the edges, at the top of the columns or the side of the rows. We're going to look at it in the body of the table. So here's a cutout of the table. It's not the entire table, but it's the chunk that we're going to need. And we're going to look for 0.2236 in the middle of the table somewhere. Can you see it? It's right here. Now, if you're trying to figure out the z-score, go to the left and look at the heading for that row, and it's negative 0.7. And then look at the top column that number is in, and that's 0.06. So that means that the corresponding value for z is negative 0.76. Okay, let's try another one. This time we want to find the z-score value with an area of 0.4562 to its right. Now remember, when we talked about the standard normal distribution table, we said that all the numbers in the standard normal distribution table represent areas to the left. If the area to the right is 0.4562, we should figure out what the area to the left would be. Okay, so we're not going to look for the 0.4562 on the table because that would be if it was area to the left. What we need to do is do 1 minus 0.4562, right? Because these are complements. So if the area to the right is 0.4562, the area to the left is 1 minus 0.4562, which is 0.5438. So that's the number we're going to look for in the table. We're going to look up the 0.5438. So here we have a cutout of the standard normal distribution table, and we're looking for 0.5438 out in the middle of the table somewhere. Do you see it? It's right here. So we try to figure out the z-score. The first two digits are 0.1. The last digit is a 1. So it's 0.11. Okay, so now why don't you try to do a practice problem? You're going to do both types. Find the z-scores that correspond to an area of 0.7454 to the left of z, and for the second one, an area of 0.9967 to the right of z. So pause the video while you take a look, and remember, you need that standard normal distribution table. So get that out if you haven't already gotten it out. And when you're all ready to keep going, hit the play button. Okay. So for the first one, because it's area to the left, we're just going to look up the 0.7454 on the table. So here's a cutout of the table. We look for the 7454. I see it. It's right there. And so we look to the left to see the first two digits of the z-score, 0.6, and right up above it, another 6. So my z-score is 0.66. Okay, so for the next one, when we're trying to find an area of 0.9967 to the right of z, what do we have to do? The areas in the standard normal distribution table are areas to the left. So if this is area to the right, remember that to compute the area to the left, you have to do 1 minus the area to the right. So 1 minus 0.9967 is 0.0033. So that's what we're going to look for in the body of the standard normal distribution table. So here's a cutout of the table. We look for 0.0033, and it's right there. So the z-score would be negative 2.72, and that would be your z-score value. So now we can find z-score values if we know the table value. But once we know the z-score values, we should be able to convert those all the way back to x values if we need to. So here's an example. Let's say we have the situation where the average, the mean, mu, is 325, and the sigma, standard deviation, is 12.3. We want to find the x value that corresponds to a table area of 0.9131 to the left. So in this problem, the first thing we're going to have to do is we're going to have to take that 0.9131 to the left and find its z-score. We're going to use the table to find the z-score. Once we know the z-score, we should be able to use the z-score formula to figure out what the x value is. So we're going to start by looking up the 0.9131 because it's area to the left on the table. So we look for 0.9131. There it is. That z-score is 1.36. Okay. So once we know that the z-score is 1.36, we can look at the z-score formula. Z equals x minus mu over sigma. If we do a little bit of algebra, we should be able to isolate the x in this equation. So we start with that formula. We're going to go ahead and multiply both sides by sigma. On the right-hand side, the sigmas reduce. So we end up with sigma times z equals x minus mu. To get the x by itself, we add mu to both sides. And so we get that mu plus sigma times z equals x. We can use this formula to figure out the value of x in our problem. So x is going to equal mu plus sigma times z. The mu in this problem was 325, the sigma was 12.3, and the z-score we just found was 1.36. We multiply, and we get 325 plus 16.728, and then we can add. So the x value here would be 341.728. So we get what's called the x value formula. The x value formula is what we just derived. X equals mu plus sigma times z. So if you have the z-score and the mean and the standard deviation, you can always find the x value that would result in those other values. So here's a practice problem for you. If mu equals 291 and sigma equals 13.7, find the x value that has an area of 0.1131 to the right. So give yourself a chance to do this. Pause the video. And when you're all ready to go, hit play. Okay, so the solution here. First, we notice that 0.1131 is not area to the left. It's area to the right. So since it's area to the right, we have to do 1 minus that area, 1 minus 0.1131. And that gives us 0.8869. That'll be the area to the left because we always look up the areas to the left on the z-score table. So we go to the table and we look for 0.8869, and it's right here, and that corresponds to a z-score of 1.21. We now use our brand spanking new x value formula. x equals mu plus sigma times z. The mu in this problem was 291. The sigma in the problem was 13.7. And we just found out that the z-score was 1.21. We multiply the 13.7 times 1.21 and get 16.577. Add this to the 291, and we get 307.577. That would be the x value that corresponds to that z-score. Okay, so let's take a look at a new example. The length of newborn babies is normally distributed with an average of 19.4 inches and a standard deviation of 1.6 inches. What is the length that corresponds to the 95th percentile? Wow, we haven't seen percentiles in a while. That was back in section 2.5. But we should still be able to do a problem like this. We just have to remember what the 95th percentile means. Remember what the 95th percentile means is that 95% of all the data values are at or below where you are. So when we say the 95th percentile, that means that an area of 0.9500 lies to the left of that z-score. So we're going to look up 0.9500 on the table. So here's a little cutout of the table. And we don't find 0.9500, but there are two values that are close. It turns out that 0.9500 is directly in the middle of these two, right? So what we do is we're going to go ahead and take their average. So what's halfway between 1.64 and 1.65? And again, if you have trouble doing that, you can always put zeros at the end of those decimals and it makes it a little easier. If you put a 0 at the end of each one, it's 1.640, 1.650, so you can think of it as 1640 and 1650. And halfway between 1640 and 1650 is 1645. So we're looking up z equals 1.645. That only applies if the value you're looking for is exactly halfway between the two that are to the left and right of it. If it's in the middle but not exactly halfway, then you're going to use whatever z-score it's closest to. Okay. So now we're using the z-score equals 1.645 in our brand spanking new x value formula. X equals mu plus sigma times z. The mu was 19.4, the sigma was 1.6, and our newly minted z-score is 1.645. We multiply the 1.6 times 1.645, and we get 2.632. Adding that to the 19.4, we find out that 22.032 is our answer. So what that means for us is that if a baby is 22.032 inches, then it is in the 95th percentile. Finally, we have a practice problem. This is about cereal. The weights of the contents of cereal boxes are normally distributed with a mean weight of 20 ounces and a standard deviation of 0.07 ounces. Boxes in the lowest 1% do not meet minimum weight requirements and must be repackaged. What is the minimum weight requirement for a cereal box? So we're going to do something very similar here to what we just did in the newborn baby problem. So pause the video, give yourself a chance to work on it, and when you're ready to hear the answer, hit play. Okay, so let's take a look at the solution. When we say the lowest 1%, 1% would be a table value of 0.0100, right? Just like the 95th percentile, 95% was 0.9500, 1% is going to be 0.0100. So that's what we're going to look for in our table of values. We don't find 0.0100. The closest thing that we find is 0.0099. You'll see that there's also 0.0102, and the 0.0100 would be between those, but it's not exactly in the middle. Because it's not exactly in the middle, we use the one that it's closest to, which is 0.099. So that 0.099 has a z-score value of negative 2.33. It's that value that we use in our brand new x value formula. X equals mu plus z times sigma, which is 20 plus negative 2.33 times 0.07, which ends up being 20 minus 0.1631, which is 19.8369. So the minimum weight for these boxes is somewhere around 19.84 ounces. Anything less than that, and the manufacturer would have to pull it from the assembly line and repackage. So that brings us to an end of section 5.3. So please remember to look on Pearson for your homework, and have a nice day.